Okay, let's start. Today, the first talk is given by Guifre, Vidal. He's going to talk about efficient classical simulations. And we tried a lot of quantum, but also we tried classical, semi-classical gravity. So, but this is semi-classical many-body localization.
Maybe. All right. Thanks, Xiaogang. So I'll start by thanking the organizers, Frank and Ignacio, for the invitation to come and give this talk, for organizing the workshop as well. And yes, I want to talk about efficient classical simulation of quantum many-body systems with local integrals of motion. That's the longest title I could come up with. And this is work that came out of discussions with Anusha Chandran and Isaac Kim, two postdocs at Perimeter, and also Dima Avanin. And maybe I want to start by saying that there is a physics motivation for this talk, but I'll quickly forget about physics. So the physics motivation, is many-body localization. And so for those of you who are not familiar with the subject, this is about the disordered quantum phase of quantum matter, where there is this localization going on. That means there is no transport. That means for us that the whole spectrum of the Hamiltonian is made of states that are almost a product state. Okay, and then there is a long history, but I feel very lucky because Bella will give a talk tomorrow about probably including some physics. So you will learn about the I don't know, electrons and things. So, but let me say then that there is a long history of localization. So this goes back to Phil Anderson. In 1958, and what this work started was single particle localization. And so the observation there was that if you have a system of free fermions with some local Hamiltonian and you introduce some random magnetic field, you can end up in a phase where all the single particle wave functions are localized in space. Okay, so if you have a translation invariant system, then you have a band structure and you have that eigenstates of the Hamiltonian are spread all over the system. But if you have localization at the level of single particle, then single particle wave functions cannot move or are localized within some region of space. And then you build a whole spectrum in this case by just the usual free fermion construction. So you end up with a spectrum which is made of, the basis is just single particle wave functions that are localized. Now, many-body localization is the interacting version of this. So what you do is you try to understand whether when you add interactions to your Hamiltonian, so when you go beyond free fermions, whether you still have such type of structure in the spectrum of the Hamiltonian, whether your states are localized in some sense. And here it's a good place to say what sense this is. This would be whether all the eigenstates of Hamiltonian are short-range correlated, close to a product state, or can be deformed to a product state. That would be in absence of topological order. Then you can superpose this with topological order. But I won't go there. I'll assume that we don't have topological order here. All right, and I want to mention that there are lots of people who have worked on this many-body localization. That roughly started around 2005 or 6. I learned a word last night, rekindle. I forgot the meaning, but the sentence was that the interest in localization rekindled around this 2006 because there were observations that maybe if you add interactions, you still keep localization. And since then, there have been many people contributing to that, and I was shocked how many people are here today, so I made a list of the ones that are here. Then I realized they are recording this, so I apologize for all people I'm missing. But of course, we have Bella Bauer, who will talk about this more seriously tomorrow. Then Frank Pullman might be. This is like checking who's here, right? So Frank, Frank. Okay. So Frank. All right. So local people like Joel Moore, Brian. Right. So Brian has worked on that as well. Thomas Prosen. Thomas. Yes. And Jens. Hey. Yeah. Okay. And many other people. So sorry if I forgot somebody, but. And I've been working on this, for the last 2 weeks. So one thing I noticed with discussions with Anusha and Isaac and Dima at Perimeter is that all the work that has done so far, most of the work that has done so far, at least most of it, is using exact diagonalization, right? And so in this type of problems, we don't want to work or study the ground state. We want to study the full spectrum. Okay, so we cannot use simple, how do you call this? You have to study the whole Hilbert space, right? So you cannot say you study 30 spins, right? You have to. You cannot use Langsos or some simply. So it's not enough to describe one wave function. You want to describe 2 to the n wave functions in a spin system. Okay? And so this means that the system sizes that you can study with exact diagonalization are rather small, say 10, 12, 14, and you start getting tired pretty soon. So what I would like to do in this talk is to explore the possible use of tensor networks to study these problems. Okay?
But there's an issue about whether ground state have a localization or not. That's an issue. Because you talk about maybe the any eigenstates. It's like a product state.
No, I'm going to assume that all of them. I'm going to assume actually.
All of them.
I'm going to assume that we're in a regime.
But including ground states then. Or
yes.
Maybe except ground state.
Including ground state.
I see. So whether there's notion that if you only get the ground state, you say, oh, this ground state looks like product state that's localized, or maybe such a notion don't exist.
I wouldn't say that you are in a localized space if only the ground state is a product state, because then the excited states may be completely delocalized. So this localization is related to lack of transport in the system, and if only the ground state is.
So basically, my question is that if you only know ground state exactly, can you say something about whether low energy is many-body localized or not many-body localized?
You might. I don't know the answer. But this is this. So I'm gonna deal with a very specific question to make it well defined, and it's not gonna be this one. So what do I want to deal with here? So we're gonna have a lattice. In d dimensions, and we'll have n sides, and each side is going to be d level, and so the total Hilbert space is going to be tensor product of those sides, n of them. It's going to be square, hypercubic, or whatever. That's right. And that, just to make things concrete, it could be anything else. And what we're going to have here is a local Hamiltonian. And by local, I mean that I'm going to assume that it acts, so if this was in 2 dimensions, and these were the sides of our lattice, it's the sum of terms that have some finite support, local support. So I'm not looking at exponential tails, exponentially suppressed tails, or anything like that. And then this Hamiltonian, in the context of many-body localization, may have this order, number of properties, but I'm not going to worry about it. I'm not going to specify it, actually. What I'm going to demand is that it has, local Hamiltonian H, and we want to have n, a complete set of local integrals of motion. Okay, and so what do I mean by integrals of motion? So I'll take care of the local part later, but just to be clear, so we said that we have these integrals of motion. I'm going to denote them by z and some index n. N is going to run from 1 to n. And what I mean by integrals of motion is a set of operators, Zn, that commute with the Hamiltonian and commute among themselves. Okay, so that's a very...
N capital the same like number of the sites?
Yes.
Thank you.
Yes, and that's going to be concrete. I could change this number, but I'm going to assume that if each site is d-dimensional, I'm even going to assume that these guys can be regarded as d-dimensional in some sense. So I'm going to assume actually that these integrals of motion have each d eigenvalues, different eigenvalues, and then some projectors. So this is the spectral decomposition of these integrals of motion. And this is just notation, and I'm just going to give you an example so that, I mean, there is no difficulty here, but let me just give you a concrete example. So we could think that we have a Hamiltonian, which is just some magnetic field in the z direction, plus, say, nearest neighbor, or yeah, some sigma z couplings. Maybe nearest neighbors, doesn't really matter. Okay, so imagine we have this Hamiltonian, then a set of constants, integrals of motion could be given by each of this z is just a polymetrics acting on a different spin. Okay, so indeed, if you look, right, so z1 would be sigma z on the first spin, identity on the rest. We could have z2 could be sigma z on the second spin, etc. Okay. So in this case, it's a completely trivial example. I just want to make sure that we're not confused by the notation. So in this case, you can easily check that every sigma z commutes with a Hamiltonian, and that they commute among themselves, the z. So that would be an example. Okay. So what I'm doing here is just having a generic situation. These operators don't have to be localized. They could be acting on the whole Hilbert space of the n spins. And this is just the spectral decomposition. Okay. Is that clear?
So you could equally well, just to satisfy, the projections themselves are integrals of motion. Is that right? The individual
yes,
projections?
that's right. But I like to, so the eigenvalues actually don't mean anything here. But what I'm insisting is that we group them in groups of 6, or D, in groups of D. Right? So these projectors that you're mentioning here, I'm just putting them together. When we consider, which is what I'll do now, when we consider local integrals of motion, then I'll insist that all these projectors, these D projectors associated to Z, to a given integral of motion, they are all acting on the same region.
Do you have a particular criterion for the independence of the integrals of motion?
They have, right, so I want this to be a complete set. And so if you count parameters, they have to be independent in order to be complete. Is that what you're asking?
Well, for instance, if you just multiply 2 of them. Then
fine, you can do that. Yes, this is an algebra, right? So they form an algebra. If you multiply 2 of them, if you add 2 of them, if you multiply 1 times 3, they are all integrals of motion. So what you want to make sure is that your set is complete, and this implies that these guys are independent as well.
But I guess you want to exclude something like the eigenvectors, the projectors on the eigenvectors.
No.
Because that's obviously a complete set of integrals of motion.
Yeah.
That's right. Well, that's what.
Yeah, no. I mean, this is all obvious. I'm just giving you time to get used to the notation. And when you insult me a lot, then I'm
still not sure what you mean by locality. So what is
D? Yeah, there was no locality yet. I'm going to add locality.
So what is D? I missed the...
D is some... Okay, so we have a D here, which is the dimension of the... So we have n sides. Each side is a D-level system.
Okay.
And just for concreteness here, I'm going to assume that the integrals of motion are also D-level. Right, so each of them can be expressed as d different projectors.
They're just these d distinct eigenvalues.
Yes. Yeah, that's the
assumption.
And so in the example, d is equal to 2, and you can see. Right, so if you look at this as an operator acting on one side, then it has two different eigenvalues, but the rank is, well, there are only two different eigenvectors, but if you multiply times the identity, then you degenerate. Okay?
Do you have a situation where integral motion, number of integral motion is much less than number of lattice side?
You could.
So here is about the same.
No. Here I'm assuming it's a complete set.
I see.
So I'm assuming it's the same. And you can relax many of these things. I'm just trying to go for the simplest scenario. Okay. All right. Perfect. So locality. So, oh no, before that. So I'm going to insist that this is a complete set of integrals of motion, and in particular, what that means is that if we look at the Hamiltonian, then we can find a complete basis, a complete set of eigenvectors of the Hamiltonian that correspond. So I'm going to use mu here as a vector with mu1, mu2, mu_n. This vector chooses for each integral of motion, you choose one option, right, in this sum. So it's a choice of eigenvalue, if you want, for each integral of motion. So I'm going to choose one eigenvalue for each integral of motion. I'll make a vector with those. And then what I'm saying is that you can characterize every eigenvector of the Hamiltonian with a string of mu's. Okay? So you can completely characterize an eigenvector of the Hamiltonian by specifying, we also have that, so what do we have? We have that z, the integral of motion n on this eigenvector of the Hamiltonian is equal to the corresponding eigenvalue, mu_n e mu. Okay?
So all C's are different. There is no translation invariance, right?
All C's. Yeah. Yeah.
Momentum, nothing like that. Shift operator.
This was just an example to really completely clarify what these integrals of motion are. This is not an example of many-body localization. It could be, but I'm not. Right. So let's not worry about whether this is disordered or not. Okay. And all I'm saying is the trivial statement that if you want, it follows from completeness of this complete set of integrals of motion that you can characterize. You can completely characterize the eigenstates of the Hamiltonian by specifying how they react, how they relate to the integrals of motion. All right? Excellent. So in this example here, that would mean that every eigenstate of H is just a product state in the Z basis, right? And so an eigenstate of H is just a string of ups and downs. And this actually, this thing here, up or down, is giving you the eigenvalue for these integrals of motion. So, well, yes, so this should be clear at this point. All right, so then let me just say the same again. I'm going to define some projector, P mu, as the product over all the integrals of motion of some of these projectors. So for each integral of motion, right, this is P1, mu1, P2, mu2. The order doesn't matter, these projectors commute, etc. Right, so I'm gonna define this projector, which is for each integral of motion, I give a particular eigenvalue. Okay, and this by construction, this is nothing but a projector onto an eigenstate of the Hamiltonian. Okay. All right. So now let's make this local. Okay. Now the statement that these integrals of motion should be local. What does this mean? So I'm just gonna demand local integrals of motion. I'm just going to assume that each of these integrals of motion can be written. I don't want to introduce more notation, so I'm just going to say that one thing is equal to itself times the identity on many sides. Okay, so I'm going to say that each of the integrals of motion is only non-trivially supported on eta z sides.
You know, for like long tails, like exponentially.
No. And right. So I'm going to assume that this is a hypercube. Actually, that's not even like this. So I'm going to assume that each integral of motion is supported on some finite region. Say in this case, this is eta z, for eta z equal to 2. Okay. So in general, we'll have eta z to the d sides, right? So these integrals of motion are really very local. Okay. And I'm not going to even allow for exponential tails deviating from that. So I'm just looking at a very, very simple scenario. The exponential tails on top of that. So in many-body localization, what the physics seems to tell us is that these integrals of motion are essentially contained in a small region, but then there might be exponential tails. I'm going to cut those. Okay. But one can argue that should not be a big thing. If that was an approximation. All right, so this is the scenario I want to deal with. I have this Hamiltonian. It commutes with all these integrals of motion, which happen to be local. And the question I would like to ask and try to answer is a very simple one. So if somebody gives you, or given this complete set of local integrals of motion, can we efficiently classically simulate the system? And of course, if I don't say what I mean by efficiently classically simulate the system, then that doesn't mean much, but I'll specify that in a bit. But I mean things like, can I compute local expectation values? Can I efficiently classically compute local expectation values for any eigenstate of the Hamiltonian? This type of questions. Okay, I'll specify a bit more later on what I mean by this. And then I was preparing these notes, and I wasn't sure whether this was a theorem or a conjecture. But I know you don't care. I mean, yeah. So I actually, it ended up being something more of a wish. But, and actually, sorry. So the question is, can we classically simulate the system? And so the theorem, conjecture, wish is that yes, of course. Sure. Okay? Because, Vladimir, this is integrable at the very least, or, it's, right?
How many of these variables you have?
A complete set. Yes. So the intuition is that everything is determined, everything is local, so yeah, why? What? And so the proof, first I started with my hands, right? You also know what that is. And I was at the level of theorem, then, and it was still sure. And then I tried to write something down and, slow down a little bit, it's a conjecture. And then well, actually, I don't know how to prove this. So I don't know if it's true, actually. Okay. But then tensor networks came to the rescue. So let me make a small table of results. So I'll talk about the spectral tensor network. I'll talk about whether we can compute expectation values for local operators on any eigenstate of the Hamiltonian. And I could probably I won't have time of doing anything, but there is, maybe I can announce that you can also consider simulating time evolution on this Hamiltonian, starting from an initial state, which is anything that you can efficiently represent with a tensor network. Okay, so we start with a tensor network, and we can, and so the question I want to address is whether I can efficiently simulate time evolution.
What about just writing down an eigenfunction given the spectrum?
Yes, so that's going to be here, and the answer is going to be yes for, yeah. That is, well, it's a theorem, yes, and I'll draw the proof. So then what I want to do is to try to look at this in one dimension and in 2 or 3 dimensions, or any number of dimensions larger than 1. And so the good news is that we can find spectral tensor. So what's a spectral tensor network? So I'm borrowing this label, this name, from work by Andy Ferris, who recently showed that you can build a tensor network for free fermions, for a system of free fermions, for the whole spectrum, efficiently contractible tensor network for free fermions. And so the idea here is to have a tensor network that can efficiently represent the whole spectrum of the Hamiltonian, right? So any eigenstate of the Hamiltonian is a particular case of fixing some indices in this tensor network. Okay, so we'll build this spectral. It turns out that in 1D you can build this spectral MPS, and you'll see it's a piece of cake. And this will be some tensor network that represents any projector onto any eigenstate of the Hamiltonian. So basically, this tensor network comes with extra indices corresponding to the mu's, right? And every time you fix the mu's, you get a matrix product operator for this projector. And you can do the same for 2 dimensions. So you can have a spectral PEPs in that case. Okay. So it's good news. You can efficiently represent all these wave functions, all of them, 2 to the n, or d to the n in this case. Now, we know in tensor networks that one thing is whether you can write something as a tensor network, and a completely different question, or much harder in general, is to efficiently compute expectation values, okay, from it. So suppose we have this spectral matrix product state. Now we can ask the question, can we efficiently compute expectation values from it? And the good news is that yes, in 1D that's not going to be a problem, and that's going to be an exact calculation. You can do it exactly, okay, with a cost that is proportional to the system size only. And time evolution, so again, in 1D, we can do this. We will be able to do that. But this requires sampling. Sampling over the distribution of so there will be some sampling. So we can efficiently sample to evaluate things like the expectation value on, say, a local operator after some time. Okay?
Starting from arbitrary initial state?
Yes. The only assumption here is that this can be represented efficiently with an MPS, and the rest is taken care of in 1 dimension, of course. So we'll have actually very nice perfect sampling strategy. So you can draw. It's a situation where you sample. You have to sample. You have to use Monte Carlo sampling techniques, but every time you draw a probability distribution is completely independent of the previous ones, and so all the samples.
Can you tell us what to sample?
Sorry?
What do you sample?
Sample.
What do you sample?
Right. So I'll be sampling over. Over this object, which is the overlap between the MPS, that is the initial state of this time evolution, and this spectral MPS. It's a projector, right, for any value of mu vector, right? So this is going to be the spectral MPS, and then I can efficiently sample. This defines a probability distribution, and I can efficiently sample over that. Okay. So what this means is that there are many things you can do, and then all the techniques.
I'm not sure I understand. So you
fix a mu and then you sample the overlap with that fixed?
All right. So no. I'll get to that. But so I'll explain that better later. But the idea is that you can always decompose this state into eigenstates of the Hamiltonian, and this will give you some amplitude, that state psi 0, an overlap with state E mu. And what you can do then is efficiently sample over those amplitudes, right? Or according to the weight given by those amplitudes. And what this does for you, it's quite nice, because usually when you do time evolution, you maybe have to simulate up to some time and then keep the simulation after a later time. Here, we run a sample, so we generate samples, and then we can evaluate over any time that you want. So you could start with time 2,000 and a million, and you would be able to sample that. So this is not time evolution MPS technique. It's you can directly sample arbitrarily large times. Yes?
The guys in the middle, how do they look like? I mean, there's this eigenstate formalization hypothesis that states if a system is not integrable, that if you're in the bulk of the spectrum, that these expectation values should take the values as if you're at a maximum entropy state, given global expectation values. That would not be true here because it's an integrable system, but would they take the values as the maximum entropy state given the local constants of motions? I mean, can you just easily compute them in this way?
Can you compute what, sorry?
That the expectation values would be maximum entropy states given the local constants of motion. Is that?
What is an expectation value that is a maximally entropy? I don't understand it.
Oh,
so the claim is that you can compute it.
You compute these quantities.
Yeah,
and compare them with the setting where you will just fix the certain maximum entropy, fix expectation values, and then take the maximum entropy state given.
No. What I'm saying is, for any eigenvector of the Hamiltonian, I can compute this value.
Yeah.
I mean,
no, but
hence, in this case, you have a complete set, so there is no. Once you specify all the integrals of motion, you specify the state.
Right. Yeah, but it's just like how does it look like? What are the values taken? We can discuss it later.
Okay.
What does that look like?
Right. So the statement. Well, I haven't applied this to any system, so I don't know how it's going to look like.
Oh, that's the question.
Right.
Okay.
So I have not used this in the context of many-body localization.
Okay.
Because I mean, I'm assuming that I have this complete set of integrals of motion, and an independent problem, which is something we're working on, is how to determine this complete set. Right?
Okay.
So here what I'm assuming is that we already have it, and then given that, I'm exploring what we can do with that. Okay? Good. So and then the idea is that in 2 dimensions you can again build these spectral peps for the whole spectrum of the Hamiltonian, but when you try to compute expectation values, well, if you cannot prove that you can do that efficiently. So you can write the peps for this expectation value, and then you can try to use the usual techniques with peps to to approximately contract the tensor network, and if that works, then you have a scheme. But of course, I cannot prove that this, or I'm not able to prove that this is going to work. Okay, so the answer then is that we don't know what's going to happen in here. It might be the techniques can be applied in principle, whether they will work or not. It's something I cannot prove.
So you can probably do that NP hard at least, no?
Right. So NP hard or QMA. I don't know. I expected some fancy name to appear during the talk, but maybe you can. I mean, the restriction here is that these integrals of motion are local, and maybe that allows you to run away from this. But I don't know.
But like if you take a classical spin glass,
right?
And you know all these integrals of motion, but you don't know the states. So this is a PEPS.
Okay.
And this is at least.
So in a classical case, right? So in a classical case, we don't know even for nearest neighbor or local Hamiltonians. That's not known.
So in a 2D classical case would be NP hard.
Yes. So as I was saying, no. I mean, this morning I thought. Oh yeah, no, that's okay. All right. So. Sure. I expected this question at the end. Sorry?
That exists in some cases.
You could build this to be a spectral mirror. Oh, you mean it already exists with this?
I know examples where a mirror generates the entire spectrum.
Sure. You're right. I have a comment on that, but I was going to get there in a while. All right. So, good. So I had a plan, which is time to revise. So what I'm going to do I'm going to just mention that that you can do much more than this, and that's what I was trying to do initially. Okay, the original theorem was to prove that you could do everything, and in which setting is that possible. So it turns out that if you have a complete set of local integrals of motion, okay, these z's. Okay, if you have a complete set of local integrals of motion, and on top of that, you have a complete set of local conjugate variables to those, and probably I won't have time to define this, then you can do anything you want in any dimension, okay, efficiently. So you don't need tensor networks, you don't need anything. So anything you want means that you can, in that case, in any dimension, you can compute expectation values of these expectation values for local observables for any state, eigenstate of the Hamiltonian. But you can even explicitly, given a local operator, you can explicitly and efficiently build its time evolution. Okay. So you can, if you have not only local integrals of motion, but a complete set also of local conjugate variables to those, which I haven't defined, then basically you have a complete characterization of another factorization of your Hilbert space, right? So remember we had this Hilbert space in terms of size I. So if you find not just these local integrals of motion, but also a complete set of local conjugate variables, then you can define another factorization of the same Hilbert space, which is related to this one by some locally generated unitary. Okay? And then you can do many, many things. And Brian, you're looking at me. This would be the one that you describe in your work.
Can you just say, like, briefly what local conjugate variables? So these z's actually don't completely characterize a tensor product structure of a Hilbert space, because you have all the, they only generate the diagonal part, right? So you need some conjugate variables that will allow you to move between the eigenstates of this guy without touching the rest of eigenstates, right? So you need some conjugate variables that commute with the rest of integrals of motion and only don't commute with this one and allow you. It's like creation. Sorry. And they have to be local, right? So this is actually, these are the responsible for why we need to resort to tensor networks here. If you don't have those, then many things can go wrong. Okay. All right. So great. So I'm almost done with introduction, and let me start. So where's the? Okay.
At the end, there will be some specific constraints on the C's in the Hamiltonian. I mean, the requirement that everything should be efficiently simulated by tensor network, that this requires a specific set of C's in the Hamiltonian.
I'm not gonna talk about the Hamiltonian. I'm just assuming that this Hamiltonian is such that it has a complete set of integrals of motion, and that's all I need to say. All right. So spectral. So what's this? A spectral tensor network. All right. So I'm just gonna in 1D. I'm gonna specialize to 1D directly. I mean, this construction is valid in any dimension, but I'm going to assume that we're in 1D. And remember, I said this guy was local, so it acts as the identity everywhere except in some region, and this region has size eta z. Okay. So you can actually write this operator in this form. Okay, and the assumption here is that this operator is given to you, this 4 spin in this case. So this is eta z equal to 4, right? This is where it's localized. And so I have one thing I have to mention here is that if you can show, it's an easy, simple lemma, if all the integrals of motion are local, in the sense that we said, then there is a finite density. Finite
density of such integrals of motion anywhere. So what I mean by this is that if you look at a particular spin or a particular side of your lattice, say this side here, then there is a finite number only, independent of the system size, of integrals of motion that can be acting non-trivially on that side. Okay? And this is something that you can argue easily. Maybe it's even easy to do in 2 dimensions. So all I'm saying is that, so yeah, let's do the 2-dimensional case. So what I'm saying is that suppose that we have we consider one given side in 2 dimensions, say this side here, right? What I'm saying is, I'm asking the question, how many integrals of motion have support on that side? Okay, and I'm going to assume, say, that each integral of motion is supported on eta z equal to 2, so eta z square sides, right? And so here's an integral of motion. Now, here could be another integral of motion. And maybe here we have 2 of those. Nothing prevents us from having that situation, right? But if you look at how far away from the side we can go, obviously we cannot go too far away. So what I'm saying is all the integrals of motion that overlap with this, right, are contained in a larger hypercube. And this hypercube has size 2 eta, what was that, z, minus 1 times, so you can just check that if you try to place hypercubes here, or squares in this case, that overlap with this side, then you cannot go too far away from this side. And so the idea is that we end up with a region we can have a look at the region. This region is the region where integrals of motion contained in the region may overlap with this side. And then what we see is that, well, how many sides do we have inside the region? So the number of sides q inside the region is just 2 eta z minus 1 square, or general d, right? And so we have this finite region. And now in this finite region, how many integrals of motion could we possibly have that are contained in it? Remember that these integrals of motion have to be independent. So at most you can have this number. Okay? So you cannot have more integrals of motion inside. You cannot have more independent integrals of motion inside the region than this number, because otherwise you would have more integrals of motion than degrees of freedom. And so this tells you that overlapping with the given side, you can have at most this number of integrals of motion, right? So, and this number is independent of the system size. So what we learn is that we cannot have many integrals of motion acting in any given point. Okay, so that's good. That's good because it means that we will not have an accumulation anywhere, and so now we are ready to just write the efficient representation in terms of a spectral matrix product state in 1D. And so I'll do this here. So if I want to represent a projector P mu, which was a projector onto an eigenstate of the Hamiltonian, then all I need to do is to draw lines for all the qubits. And remember, each projector is contained in the support of an integral of motion. So the first one maybe comes here. That's just a pictorial representation. You can prove all these things. I'm just trying to give the main idea. Right? So what we have is that the first projector would go here. The second projector would go here, and there is an extra index mu2 coming out, mu3, mu4. Okay. Remember, this is nothing but a product of projectors for each of the integrals of motion, right? So I'm just drawing each of those guys, and each of those can be represented by some tensor acting on a small number of spins. Okay? And so I just keep covering all this. And when I get tired down here, I continue up here, maybe one more. And the idea is then that you can cover the whole lattice. And I insist that I'm just assuming that they are equally spaced. That's just a simplification. They don't have to, but there is a finite density, and that's all I need. Okay? So on each point, I don't have more than a certain number of integrals of motion acting on it. And so all I need to do now is, for each of these projectors, I just compute an MPO. I just decompose it as an MPO. I put it in here, right? And I multiply many indices, and after a lot of effort, multiplying these indices, you end up with some MPO with extra labels, mu1, mu2, mu3, mu_n. And this MPO, which has finite rank here, because this rank is the result of multiplying many ranks, but a finite number of those. Okay, this MPO is exactly what we were after. Okay, it's the spectral MPS that we wanted for this case. So this MPO is what? It's a map from these indices here. Oh, I promised myself I would use another color for those. So we have two types of indices. Okay, the black ones correspond to spins or sites in your many-body system, and the red ones correspond to these integrals of motion. Okay, and this object is for every time you specify values for these indices, you get a particular projector into a particular eigenstate of the Hamiltonian. Okay, and this you can do it in any dimension, and that's it. And the only trick is to remember that there is a finite density of integrals of motion once you enforce that they are local. Good. So I'm going to call this spectral MPS, and we can do this in 2 dimensions. We'll get in spectral PEPs, and now it's a good time to compare this to things that we already know. So, for instance, if you give me the toric code, okay, the toric code is the Hamiltonian is a set of commuting observables, and you could take those directly as integrals of motion, right? And you can actually build a PEPs for the ground state, but actually for the whole spectrum of the toric code. And this has been done, has been used, and it's common practice. Maybe the observation here is that there is a difference between that. Well, in that case, we would have to talk about topological order, but the fact that the set of local integrals of motion is not complete. There are non-local integrals of motion corresponding to the topological qubits, but that's not the point. The point that I'm trying to make is that in that case, we're using a spectral tensor, or we could build a spectral tensor network that would become invalid as soon as we perturb the Hamiltonian a little bit. Okay? So in the toric code, in a fixed point, in general, in a fixed point wave function, whenever we have a fixed point of the RG flow, you may have that the spectrum of the Hamiltonian is very degenerate. There is no dispersion relation. It's a flat dispersion relation. And this allows you to choose integrals of motion that are local. Okay? But this disappears as soon as you put a small magnetic field. You put a small magnetic field, the dispersion relation is no longer flat, and then the integrals of motion are no longer local. So what's interesting about many-body localized phase is that the presence of local integrals of motion is robust. Okay? That if you modify your Hamiltonian just a little bit, you still have local integrals of motion. So this is not an artifact of being in a fixed point, RG fixed point Hamiltonian or wave function.
But if I naively I would expect I can have this conservative quantity which are only local in the instrumental sense, but will that violate this?
So what I'm discussing here now, for simplicity, is the case where they are strictly contained. So if you want, it's an approximation where I ignore these exponential tails. I can account for them at a price. So actually, this spectral tensor network, this spectral MPS, is efficient. The bond dimension is efficient for if you fix the localization, the right? The range of the integrals of motion, but it grows exponentially with this range. So this bond index here grows exponentially in the range of these integrals of motion. So if you accept certain approximation, then you can efficiently compute everything you want. If you want to consider more part of this exponential tail, then you have to pay exponential price, right? The price will grow exponentially. However, the good news is that if you look at the simulations in the context of many-body localization, the price that you pay by cutting these tails is that instead of, say, at long times seeing that the entanglement grows as a log of t, it would saturate. But it would take exponentially large time for you to see that. Okay, so yes, sure, you're approximating something, right? But it's these small corrections at very long times that you are going to suppress. Okay, good. So right, and another difference with respect to, say, the toric code, where we would have all these commuting Hamiltonians. So the first difference is, in the toric code, you introduce a perturbation, you change a little bit the Hamiltonian, you lose this locality of the integrals of motion. In the many-body localized phase, you don't. So this is an ansatz that is can be used for the properties of these ansatz, or that these ansatz exploits are robust in a many-body localized phase. And the other thing is that we are not assuming here that the Hamiltonian is written as a sum of these integrals of motion. We are not assuming that. The Hamiltonian doesn't have to, in the toric code, the Hamiltonian is just the sum of this plaquette and star term, right? Here we are not assuming that the Hamiltonian is a sum of these integrals of motion. It can contain also products of these integrals of motion, arbitrary number of products. Okay, so, well, I see that I won't have a lot of time to do anything else, but that's fine, because, yeah. So the other part I wanted to discuss is this time evolution, okay? And maybe I'll just point out how you can do this. So the idea is once you have this, oh, I have not even discussed the, all right, so need to discuss the computation of expectation values for local observables, but this now is piece of cake. So what you can do is simply, what would be this? What's the expression for the expectation value on a local operator? Well, this is nothing but the trace of P mu on O. And so P mu is this spectral guy. With these additional indices. And now, so this will be P mu with the indices that I'll draw when I get to the red. And then here, O doesn't even need to be a local observable. It could be an MPO. If it can be represented with an MPO, we can also plug it in here. Okay, and then we take the trace, right? And so this calculation can always be, this tensor network can always be computed efficiently. I don't know what that is. So remember, we have extra indices corresponding to the mu's. And every time you specify a mu, you can then efficiently compute this tensor network. Okay, so this is expectation value. And in particular, you can use this to compute the energy or anything you need to. Right, so okay, so maybe then what I want to mention is from this spectral tensor network, you can compute other quantities, and in particular, time evolution is nice. So for the time evolution, what we want to do is we have some initial state, psi 0, which I'm going to assume that I can represent as a matrix product state. Okay, that's my assumption. So this includes product states. So in many-body localization, a typical numerical experiment is you start with the product state and see what happens as you evolve in time. So here we can do that, but more generally, the initial state is not going to be necessarily a product state. It can be a generic matrix product state. And so from size 0, then we can study what happens when you apply the Hamiltonian, the exponential of the Hamiltonian to it. So we time evolve this. And in general, then we can introduce a resolution of the identity in terms of these projectors onto eigenstates of the Hamiltonian. So this becomes sum over mu. Okay, and the good news is that we may not know how to compute directly all this superposition, but there are elements in here that we know how to compute. For instance, I already discussed this. This thing here is the energy, right? The E mu is the expectation value of the energy of the Hamiltonian for an eigenstate of the Hamiltonian. Well, this is of the form that I just discussed, right? This is replace O with the Hamiltonian, which can be expressed as an NPO. So we know how to compute this guy up here. And the interesting part is that this defines some weight, this overlap between an eigenstate of the Hamiltonian and this generic state that we represent with an MPS. This defines a weight that we can efficiently compute. Okay, how does this work? Well, this is nothing but a projector onto this guy and then overlap with matrix product state. Okay, and now I just have to draw something else similar to what I just did. So this is going to be psi 0, the MPS. Then I draw here the projector onto an eigenstate of the Hamiltonian, and then the bra for the MPS, right? So this is P mu. And as usual, or as before, we have these extra indices coming out. Mu1, mu2, mu_n. And what's nice about this defines a probability distribution, which we can sample over. Okay, but it's not just a probability distribution. It's actually a probability distribution. So let's define this as P of mu given psi 0. You actually have a matrix product state form for it, right? If you contract all the indices here, you end up with just the mu's. And so again, you have an efficient matrix product state representation for these weights. Okay, and it turns out that given this, you can actually you can generate probability. So you can generate configurations mu. This is not, I'm not explaining this here, but that corresponds to previous work. It's well understood that if you have an efficient representation for this probability distribution, then you can generate configurations mu. That is, you can generate eigenstates or choose eigenstates E of mu with this probability distribution. Okay, so you can plug all these things that we knew from tensor networks into this algorithm, and you can efficiently sample, okay, at arbitrary times. So the idea is you generate a number of samples, you evaluate some expression, but you can you imagine you generate L samples at a cost. Each sample is going to cost you order n, okay, system size, and you can use these L samples to evaluate this say expectation value of. So you could ask questions about how much is this expectation value for a local operator. That's a particular question you could ask. You can use these L samples to evaluate this at any number of times. So you can reuse the same samples to follow the whole functions of, this is a function of t. So given L samples, you can just evaluate this function at any value t. Okay, great. So this was a bit sketchy, but the idea is that we can use tensor networks to help investigate questions in many-body localization. And the part that I didn't discuss, I was hoping I would not have time because it's rather involved, is the second part where I said this is all we can do without conjugate variables. But actually, if we have conjugate variables, then it gets more exciting. The bad news is we don't need tensor networks for anything. The good news is, well, that you can perform all these tasks efficiently in any dimension and without sampling. All right, so how could this be useful in current efforts in many-body localization? So far, the status of the field, one of the things that we're trying to do in many-body localization is to find these integrals of motion. There are several authors or several teams trying to find efficient ways. If you give me the Hamiltonian, right? This is a problem I didn't discuss here. If you give me the Hamiltonian, can you find these integrals of motion, these local integrals of motion? I have not dealt with that here. So this is an ongoing research effort. And the results, what they point out is, well, first, if you find them, here's what you can do. Okay? You can do a number of things. But it also draws the attention to the fact that maybe you don't want to just find these local integrals of motion, but the search should be redirected to finding not only the local integrals of motion, but also these conjugate variables. Because the number of the ability to simulate those systems then it's much larger. Okay, if we have this integral, these conjugate variables as well. Okay, thanks.
Question, comment?
A couple of questions. First, when you said spectral PEPs under 2D, is that a matrix product operator and not a?
You can think of it as some tensor network in 2 dimensions.
But it's actually implementing the projection?
Where, so there are 2 sets of indices, one's corresponding to physical sites, bra and ket, so that would be a pepo or whatever, and then extra index corresponding to
the different
integrals of motion, a different set of indices, right? So I don't know how you want to call it, but yeah, yes, no, that would be the object.
And then just a separate, different question for the. Let's see. Certain systems, presumably, can you characterize the systems in addition to being able to simulate them for things that have local conjugate variables, in the sense that we know the structure enough to sort of say these ones will not have local conjugate variables?
Right. So I suspect that one can write some theorem that says that a Hamiltonian has this structure where you can find a complete set of local integrals of motion and conjugate variables, even only if there is a finite depth quantum circuit that takes this Hamiltonian and brings it into the one that, a diagonal one. So
just one local.
They don't have to be, so no, one that is expressed, say, in the z's directly, right? So products of z's. So, sorry, the example I gave before was sigma z's. So I'm not saying it's a product Hamiltonian. I'm not saying it's a sum of just magnetic fields. It can have interactions at all orders. So it can have 2 body terms, 3 body terms, right? So I suspect that this is a complete answer. That anytime you find a complete set of local integrals of motion, local conjugate variables, then you can actually. This Hamiltonian is coming from taking a diagonal Hamiltonian of the form I just described and applying a finite depth quantum circuit to it.
Okay, so the locality of the integral of motions is only a sufficient condition for things to work, right? So everything would still be fine if we can find a system of integral motion, so that at the end the spectral we have a spectral MPS, right? So and which is efficiently contractible, like the tree width being small, right? So what you're doing here is to ensure So the locality implies that the path width is small. But maybe
Locality implies efficiency in the description.
right, and there are more general spectral MPS that could be efficiently contractible, right? For example, it's like a tree, and then the path. When you write this path, maybe the width is very large, but when you draw it as a tree, actually it's the tree.
All right, so that's Brian's question. So you could actually generalize this. You could assume that you can use a tree, you can use a mirror. So you can combine this idea with other tensor networks.
Yeah, so maybe I'm trying to say that for the question that you say you didn't have time to explore, like looking for local integral motions, maybe there's a broader question that it doesn't need to be local.
I agree, and you can allow for, so if you find that you have some density of short-range integrals of motion, and then some density of large, so every time you have local integrals of motion, if the conjugate variables are also present actually, then you can remove those from the description of the system. So there is some RG flow going on. It is not on energies, but on scales only, on length scales. So you can actually, once you identify some local integral of motion and conjugate variable, it's like a qubit sitting there asking to be removed from the description. And if you can do this here, this there, and so on, then you may be left with a system that has integrals of motion at the longer length scale. But since you've removed some of those qubits in between, now this has become shorter. And so you can have some RG flow or some RG scheme or some RG construction of this sort.
So I'm going to explain what
Maybe last question.
No.
I guess it's both to Frank and you. I'm not sure that I agree with the statement that this is indeed hard, simply because the expectation value that you're estimating is parameterized by mu, not by the ground state of the Hamiltonian, right?
So what is NP hot is actually just to decide whether this perhaps is zero or not. That's the NP hot. So I give you this PEPS, and the question is it zero? And that's NP hot.
Zero, you mean the overlap, or?
Yes. Whether they're compatible with each other, these projections.
Sure. Okay, I think it's a coffee time. And let's thank speaker again.